Hello, stats students. Welcome back. Today we are going to continue section 10.2, comparing two means. So yesterday we looked at T procedures to make a confidence interval, and today we're going to look at significance tests for two means. So let's take a look. So like we talked about, yesterday with a t statistic, when we standardize x bar 1 minus x bar 2, we get a two-sample t statistic. So to calculate a test statistic to do a significance test, you need to do statistic minus parameter divided by standard deviation of statistic. And the standard deviation of the statistic is going to use S instead of sigma. That's going to use the sample standard deviation instead of the population because we don't know the population standard deviation for group 1 or group 2. That gives us a t statistic from a t distribution. Then to find the p-value, we use the t distribution with the degrees of freedom, again, just like yesterday, either given by our calculator or using a conservative approach of the smaller of n1 minus 1 or n2 minus 1. So this gives us a new inference method. This is called a two-sample t-test for the difference between two means. Two-sample t-test for the difference between two means. So again, random, normal, independent conditions are met. Then the hypothesized value, the null hypothesis, will be that mu1 minus mu2 is some hypothesized value. We compute the t statistic using this formula. And then we find the p-value by finding the area under a t distribution with, either technology given degrees of freedom or the smaller of these two degrees of freedom in the direction specified by the alternative hypothesis. And then here are your options for the alternative hypothesis. It can be greater than your hypothesized value, less than your hypothesis value, or not equals, and then you've got a two-tailed test. And of course, our calculators can do this as well. So that would be a two-sample t test. So on your calculator, if you go stat, test, and a two-sample t test is right there, option 4. And then you've got this option of data or statistics, whether you're given the raw data or whether you're given just summary statistics of both samples. So let's take a look at an example here. Does increasing the amount of calcium in our diet reduce blood pressure? So examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 of the men received a calcium supplement for 12 weeks, while the other control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic, that's the top number, blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative response. So an increase in blood pressure is going to be a negative response. So basically, positive numbers mean we reduce their blood pressure. So more positive numbers are better. So here are the two groups. You can see the 10 people in group 1 and the 11 people in group 2. And then here's a graph of those two dot plots compared to each other. So we're going to use our 4-step process. We're going to start with state. In state goes our null and alternative hypothesis. You could write it either one of these ways, like that or like that. The null hypothesis is that mu1 minus mu2 is 0. That's no difference. That means that these two groups don't make a difference, and they're going to have the same average. That's the null hypothesis, and you can write that like that. That mu1 is equal to mu2 means the same thing as that. Or that mu1 minus mu2 is greater than 0. That mu1 is greater than mu2. That means the calcium group is bigger than the placebo group because we think the calcium group actually does help reduce blood pressure. So I have an idea of a direction in mind ahead of time. So I'm got the alternative that this group will have an average that is bigger than this group. So you could write it that way, or you can write it that way. Then also in the state, we need to define those two parameters. So I need to talk about what those two mean. What does mu1 mean? What does mu2 mean? mu1 is the true mean decrease in systolic blood pressure for healthy black men, like the ones in this study who take a calcium supplement. mu2 is the true mean decrease in systolic blood pressure for healthy black men, like the ones in this study who take a placebo. And we're going to use our significance level of 0.05. Next, we go on to the plan. I'm going to state the type of inference method that I'm using. That is called a two-sample t-test for mu1 minus mu2. Then I'm going to check conditions. Was the random condition met? Well, we didn't get these subjects from a random sample. However, we did randomly assign them to groups, and that takes care of our random condition. The 21 subjects were randomly assigned to two treatments. Next, the normal condition. So are these sample sizes at least 30? Oh, no, not at all. 10 and 11 are not at least 30. So what do? Well, I look at the graphs of the samples and I try to decide, okay, is there evidence of strong skewness or outliers? Well, from this graph, I might not know. So what I'm going to do is I'm going to make and look at some more graphs. So I'm going to make box plots, and you can use your calculator here. Go to stat plot. Well, first you have to enter your data. I already did that. Go stat, edit. There's my data for group 1. There's my data for group 2. Then I go to stat plot. I'm going to make plot 1 be a box plot showing outliers of list 1. And then plot 2, stat plot. Oh, you hear my dog? Oh, it's okay, Archie. You're okay. Then I'm going to go to plot 2. I'm going to turn it on, and I'm going to make that same box plot, but this time of list 2. When I hit graph, I might not see what I want, so I hit zoom 9 to set a good window, and there are these two box plots here, which you can see I've got pictured here as well. Do I have skewness? Oh, Archie, it's okay. And sorry about that, my dog wanted attention, so I played with him for a little bit, and now I'm back. So I think we left off here. The box plots don't show any outliers, and maybe some skewness, but nothing major. And then you can also make normal probability plots is another way to check. So again, normal probability plot. I'm going to go to plot 1 here. I'm going to change it to, and the normal probability plot is this last option here. Okay. And then I'm going to go ahead and also turn off plot 2 because I just want to look at one thing at a time here for this one. And when I hit graph, I might not be able to see what I'm interested in unless I change my window. So zoom 9 again, and that's how your calculator can make this graph right here. You can see, there's some curvature there. You might be a little concerned about this data. Can you imagine a straight line going through there and being pretty good? Maybe. Let's take a look at the other group. To make this graph right here, again, I'm going to go to stat plot, and maybe I'll just change plot 1 now, and just change this to list 2. List 2, zoom 9, and now this one is, for a second group, and you can see this one is definitely more of a linear normal probability plot. So what do we say then after looking at all of that? Well, something like this. The box plots show no clear evidence of skewness and no outliers. The normal probability plot of the placebo group's responses, this one, looks very linear, while the normal probability plot of the calcium group's responses shows some slight curvature. With no outliers or clear skewness, the T procedures should be pretty accurate. And then we continue. Basically, for my tests and the AP test, the conditions will always be met. Now, sometimes they might look like this, where you have to do a bit of work to check them, and they might be close, and you're going to proceed with caution, is maybe the language you could use as well. The independent condition then. Due to random assignment, the two groups of men can be viewed as independent. So again, make sure you have that sentence. These two groups are independent because they were randomly assigned separately. And then also individual observations in each group should also be independent. That is, knowing one subject's change doesn't give us any information about another subject's response. Notice I'm not checking the 10% condition because I'm not sampling without replacement here. These were volunteers in an experiment. I'm not sampling from a large population, so I'm not checking the 10% condition. Next, we move on to the do portion. So if we're using, our table, it looks like this. So we plug the numbers into this formula, get this test statistic, look it up, and we find that it's degrees of freedom of either the smaller of 10 minus 1 or 11 minus 1. So I'm going to use the smaller of 9 or 10, so I use 9, and I look for a test statistic that's going to be in between these values, which means I know the p-value will be in between these two values. On your calculator, to do that, you're going to make sure your data is typed in, stat edit, into list 1 and list 2. Okay, you then go to stat and then test, and then we set its option 4 to sample t-test. And then I have the data this time, so I'm going to select data, and group 1 is in list 1, group 2 is in list 2, leave that like that and that like that. And then what was my alternative hypothesis here? The alternative was that, let's go back to that, mu1 is greater than mu2. So I'm going to say that mu1 is greater than mu2. Pooled, always select no, and then calculate. And then you can see that using the table, we got a p-value between those two values, and using my calculator, this tells me the p-value is 0.06, which is indeed between those two values. My calculator used a degrees of freedom of about 15.6. And there are, some other pieces of information. There's the test statistic, p-value, degrees of freedom, and then here are the means and the standard deviations as well, and the sample sizes below that. So that's how you can use a calculator to get a p-value. Then make a conclusion. Since that p-value is larger than 0.05, we fail to reject the null hypothesis. The experiment provides some evidence that calcium reduces blood pressure, but it's not convincing. So we do have some evidence that, this group, that this group on average did better than this group, but it's not strong evidence because the p-value wasn't low enough. Okay. So we do not have convincing evidence to conclude that calcium reduces blood pressure more than a placebo for this group. Now you will notice, extra tip here, when we got this fail to reject decision, make sure you interpret the results as saying we don't have enough evidence to conclude the alternative. Saying anything that sounds like you might believe the null hypothesis is or might be true will lead to a loss of credit. So always put it in terms of the alternative and say we don't have enough evidence to conclude the alternative. So that's where we're going to stop for today. Tomorrow we'll look at an example of a two-tailed test and talk some more about t-tests. And I think we're going to finish up section 10.2, which is the end of chapter 10. I think we're going to finish that up tomorrow. So hopefully you've got some start on that homework already. If not, you should start that tonight. All right, and as always, please email me with any questions that you have.